I'm going to do a quick run through of how I would use the Truss Simulator from Johns Hopkins to analyze the performance of a bridge. In this case, we're taking a look at the basic Warren Truss Popsicle Stick Bridge. I tested 10 of these bridges, and I have good data on the average of amount that each one held before breaking. We're going to use that average here in this case. And I've already plugged in my design, and I've got it very accurate according to the dimensions that the bridge was in real life. And that's helpful to spend time getting that right. Once you have that design plugged in, we're going to add a load. So we'll go up here to design, we'll add, click on force, and now you choose to add a force on a node. In this case, I loaded the bridge from the center top. So we'll click on the center top node and we'll just drag down. And it's not super important right now to just to get that accurate. Because once you click, drag, and then click again, it sets the force, and then it gives you the force in the x-axis direction and also the y-axis. And so we will now scroll down to update that to what it actually was. In this section down below your grid, you have your external forces. Now in our case, we're going to put the x force as 0. That's going to say the force was just going straight down, which is what it was. And then in the y-axis, we're going to put a number, but there's a couple ways to approach this. You can put the exact amount of force that your bridge held when it broke, but you have to keep in mind that, let's say your bridge held 150 pounds, you have to keep in mind that each side of your bridge is holding half, theoretically, of that. So if your bridge held 150, you would actually want to put 75 to get an accurate look at what the forces are in each side of the truss. So if you did that, you could go up here and then click on solve, and now it gives you the numerical value and also what shows you which members were in compression and which ones were in tension. All this is super useful information, and then you can take a look at these numbers. You can see where the forces were high and where they were low. You can take a look at where your bridge actually broke and then calculate the force that caused that member or that joint to break. What I like to do oftentimes is actually, no matter what my bridge held, I would put 100 as my force. And if you do that, it allows you to think in terms of percentages. And I find this especially helpful the larger your bridge is and the more complex the design is, because it's somewhat abstract to think 57.7 pounds of force. That doesn't translate to something that I can picture very clearly, at least not right away. But if I'm thinking just in terms of overall bridge design, I can know, okay, roughly 60% of the force, the total force on this side of the bridge, is being held by each of these truss webbing members. Okay, well that's 60%. Okay, that gives me just a little bit more clear picture of what's going on in a sense of a broad overview. Also, if you come down and look at the bottom chord, you can see that the bottom chord does not hold the same amount of force along its entire length. Rather, on the outside, now this is again only because I'm loaded here in the center, the outsides of the bottom chord are holding significantly less percentage amount of force as compared to the middle. A lot of the bridges broke with a joint along the bottom chord, and there is a joint right around where these truss members come down and connect into the bottom chord. That joint is holding the combined amount of force as what is being showed here on this section and this section. So on this side of the joint, 29% of the total amount of force is pulling this way. 86% of the force is pulling this way. So that's a combined total of greater than 100% of the total amount of force on this side is being put on this joint. in my mind, that helps me see that this joint is carrying a lot of force. And it makes sense now that that was a failure point on a number of these bridges. That tells me, okay, that's something I need to address. I need to look at that area and see what I can do to increase the strength of that joint. I can look at the surface area for gluing the members together. I can look at if I needed to increase the size or strength of the material that I was using. In my case, it was mostly a joint that was breaking and not the member itself. And that's usual or common when you're thinking in terms of tension. Oftentimes in tension, it's the joint breaking rather than the member itself breaking. When you look at a compressive member, compressive would be in red, then you could look at a joint failure. That does happen, but you also are looking often at the actual member itself buckling under the compressive force and snapping. So sometimes you need to increase the actual strength of your material by increasing its size or adding resistance to buckling by changing the shape of the member or doing just different things. Decreasing the length of the member helps it resist buckling. All those types of things are things to consider. So now what I'm going to do is I'm going to, since I took the average amount of force that each bridge held and the total was 100 pounds, I'm going to go down here and plug in 50, since that's 1/2 of what each bridge held. So I'm going to be isolating and looking at one side of the truss, and it auto updates for me. And this is the actual amount of force that this joint was holding. I can now look at that. So I'm looking at about 57 pounds of tensile force caused this joint to fail in a number of bridges. And so now that I have an understanding of percentage-wise, an overall picture, I can now start dialing in, okay, I had, let's just say 1 square inch of surface area in that joint for the glue in that joint. 1 square inch, so let's say that's what I had. I now know, okay, well, that broke at 57 pounds of force. Okay, so 2 square inches, will that hold double the amount of force? Potentially. I'd have to do some testing to verify that. But now you can start really dialing in the types of changes that you want to make. Let's say I noticed that in some of the bridges, one of these members actually broke. But in some of them, it was this joint down here on the bottom. So I may know I don't need to double the strength of this joint because I have another area in my bridge where it's also roughly close to its maximum strength. So I would look at all of my failure points and see if, oh, maybe I can increase this strength by 15%, and that will now help each bridge reach its max in a different area. And then I can go and look at a different area and see how to increase the strength in each of those weak spots. And the weak spots change as you update your design and you make things stronger. So that's just a broad overview of how I would use this program to analyze the bridges that I've built, think about what changes I would like to make, and start implementing them